So, thanks for the organizers for inviting me to talk here. So, I must start with a little warning, which is that I will talk a lot about model theory, but I'll try to do it nicely. And so, yell at me if I'm not being nice. What I want to talk about is to show that there is a nice equivalent, a nice construction of prolongations in valued fields, and that it has nice enough properties that we can actually do things with it. I don't know if I'll have time to get to it, but eventually I'd like to show that you can use that construction to show that definable sets have smaller definition sets. Okay, so what are the structures we want to look at? So I won't be describing a general theory for valued field with operators because, well, we don't have one, and so what I'll be doing is mostly talk about general behavior that happens in the examples that we do know work, which are going to be the following. So we're going to want to understand, quantify free definable sets in certain families of valued fields with operators. And as always, in model theory, to do that, we'll actually be looking at the existentially closed structure. That is the structure where, when you have solutions in an extension, you actually have solutions in the structure itself. Right, so the first family we're going to look at actually appeared yesterday already. And it's the equicharacteristic zero valued field with a contractive derivation, although I think it was called small instead of contractive. But this might be this might be actually stronger. I never remember. And so a derivation is called contractive if the valuation of the derivation is always greater than the valuation of the point. And so we can easily build existentially closed models of their structure by taking a hand field where the residue field is differentially closed, and you have and the derivation acts on the coefficients, and the value group is divisible. Another case that we'll be looking at is characteristic P fields with E commuting has a derivation. So I did not give an example of an existentially closed model because it's a little annoying to write. But essentially, it's going to be a separably closed field of imperfection degree E, where the Hasse derivations are given by the derivation associated to a P basis. And finally, we'll also be looking at equicharacteristic zero valued field with an omega increasing automorphism. So an automorphism of the valued field is called omega increasing if when you take something of positive valuation, sigma is sent to something much, much bigger. And so once again, we can build existentially closed models of that, by taking hand series where the residue field is taken to be an existentially closed field with automorphism. The value group is taken to be divisible, and you have an automorphism on the value group that is already omega increasing. One of the reasons this example is particularly interesting is because we can also see it as the asymptotic theory of these structures. So Fp of t, the algebraic closure of Fp of t with the t-adic valuation, and the one extension of the t-adic valuation, and the Frobenius. Okay, so these are the structures I want to look at. But before talking about valued fields again, I'd like to give a brief overview of what about prolongations in the algebraic case I'd like to extend. So let's look at the differentially closed case. So if I have a d-variety over k, I define the dn to be the tuple x dx dnx, and then I can look at the variety vn, which is the Zariski closure of the image under dn, and I also have an infinitary version of that, which amounts to taking the limit of those VNs, the projective limit. And so what's interesting here is that I have a differential object, which is the variety V, which is completely determined by the pro-algebraic variety omega. To be fair, it's a little fancy to go to the pro-algebraic variety because if you take an n big enough for any given d variety, you can find an n big enough so that it's already completely determined by the Vn. But if we don't want to worry about having to deal with the indices, it's nice to go to the pro-algebraic object. This construction is never going to generalize to valued fields because there is no such thing as valued field Zariski closure. I mean, there is no nice Noetherian topology around that we could use. So we have to do something else. So let's rewrite that a little. So as always, we can identify a variety, or in that case, a pro-algebraic variety with an ideal by just looking at, actually, this is exactly the ideal of the differential ideal of the D variety, where we forget it's a differential ideal. And well, maybe because I'm a model theorist, but also because there are good reasons for that. Usually, we don't just want to have the list of polynomials that are zero on the set we want to look at, but we also want to know about the polynomials that generically are not zero. So what we'll actually want to look at is that set here, which actually has no more information than that set over there, but has nice properties. So which contains all formulas of the form the polynomial is zero when the polynomial is in the ideal, and the polynomial is not zero when the polynomial is not in the ideal. And actually, I wrote that. No. Actually, that's not what I wanted to write. No, sorry, I don't want to put the dn here because I want an algebraic object, so I just want the p of the x bar. I'm sorry about that. And so it looks like it's just making things more complicated, but this is a nice object which is called a complete type. So that's a collection of formulas, so that whenever we take a finite piece of it, there's no contradiction. And also such that every formula or its negation is a consequence of that list of formulas. So these are objects that we like in model theory, and if you're looking at algebraically closed field, it's really just, it's nothing more than just specifying an ideal or equivalently an irreducible variety. But this is the object I'll want to work with to generalize things to the valued setting. All right, so now let's do the exact same thing. Do I have the time? No. Oh, yes, but I don't see anything. Oh, yes, I see something. So now if we want to do that in the valued field setting, we're going to start with a valued field with a bunch of operators D. So maybe a derivation if we're in the first case, or a bunch of Hasse derivations if we're in the second case, or an automorphism if we're in the third case, and we're going to do the exact same thing, except that first I need to explain in which languages my formulas are going to be taken. So we need two languages. We need the languages for just valued fields where there is no operators, and the languages for valued fields with operators. So the language for valued fields without operators is just going to be the ring language, and then we also add this predicate, which is interpreted as so x divide y if the valuation of x is greater than the valuation of y. Except I put it the other, yeah, it's smaller. And so formulas in the language L are just going to be basic formulas are going to give inequalities of polynomials. So things of the form valuation of p of x is smaller than valuation of q of x. And then we're going to look at all the sets that are given by Boolean combination of these things, and then projections. Although projections are not going to really play a role here. And so if we add the symbols for the operator, we're going to also look at inequalities between differential or difference polynomials. Okay, and so now we can do what we did before. So let d omega denote all the possible composition of the operators in D. So if we only have one derivation, it's just going to be all the powers of the derivation. And then we can do exactly what I did before, which is that if I start with a complete type in the language of valued fields with operators, I can define the underlying valued field type, which is going to be the set of all formulas that hold whenever I plug in something where the operators appear. Okay, so this is actually a very nice construction, because remember, one thing that was nice about the prolongation construction in DCF0 was that we got an object without derivation that completely characterized the object with derivation. And this is exactly, if we look at the first class we wanted to look at, so existentially closed valued fields with a contractive derivation, this map is injective, and so this is Canslon's elimination of quantifiers. If we look at the second class, so there is a little something subtle happening, which is that the underlying field is not algebraically closed, but the type P omega has a unique extension to a complete type over the algebraic closure, and the map P to P omega is injected. And so this is exactly Delon's elimination of quantifiers. And in the last case, sadly, this map is not injective. Because, well, indeed, the corresponding map on the residue field, which is a model of ACFA, is not injective. So I'll come back later to why this is, well, I might come back later to why this is a problem or not a problem. Okay, so this is the first part of the picture, but if you remember, one nice thing about the algebraic case was that actually we were talking about varieties, which are objects, which are finitary objects, and now we're talking about types, which are potentially very complicated objects that have a lot of information. So what we would like to do is to work with well, nicer types which somehow do not encode too much information, and so we're going to do that by looking at definable types. I'm sorry. So what happens in algebraically closed field? Well, if you have a type, you can do what I did earlier backwards, which is from the type find an ideal, and from the ideal find a variety. And now for any variety over K, we have that X is in the variety W if and only if V is inside W. So from that you can see that actually you can express by a formula when formulas are in the type. Right, so this is going to be a very important property, which and this is what we call a definable type. So a complete type P over M is said to be definable if whenever we have a formula xy in variable xy, we can find a formula in variable y, potentially with parameters, such that for any tuple, the formula phi of xa is in P if and only if theta of A holds. Right, so if we go back to what was happening in algebraically closed field, if we take phi to be a family of algebraic varieties, well, the formula theta is going to be V is inside the particular fiber we're looking at any given moment. Just for technical reasons, I also want to define that P is defined over a certain subset A of M if all the formulas theta have parameters in A. Okay, so as I essentially just proved, although there is some more work involved, but let's pretend I've proved it. In algebraically closed fields, every type is definable. By a very similar argument, every type in a differentially closed field is also definable. In valued field, this is not the case at all. There are many types that are not definable, but there are also a large collections of types that are definable. So if you look at the generic type of a ball, which is the type that says, I'm in the ball, but I'm in no strictly smaller subball inside of it, this type is also definable. Okay. So now, what happens when we try to take the prolongation of a definable type? Well, if we just look at the definition, if I take a type P, so an LD type P, which is definable, and I look at an L formula, which is going to be what's in P omega, then a priori there is an LD formula theta that tells me when this is in p omega. Because I'm just applying the definition for p itself. But if we look, there is something a little weird happening, which is that now I'm concerned with types in the language without a derivation, but somehow my formula to define the type still has the derivation in there, which is very weird. And a priori, there is no good reason why we should be able to find a formula that does not contain the derivation in it. Well, there is no good reason, but in the three cases that we're interested in here, we can actually do it. So in that particular case, everything in those three cases, everything goes well, and we can actually show that the type p omega we obtain can be defined using a formula that does not use the operator symbols. So so this is good news because it tells us that the object we get at the end is one of those nice definable types and is not one of those weird, is not a weird hybrid object that still uses the derivation or the operators to do things. Okay, so so this is all very fine, but remember what we were interested in to start with was definable sets. And somehow now we went to more complicated objects with types, and we proved nice things about types. But these nice things are only going to be relevant if we actually have a lot of definable sets around, definable types around. And so if you look a little at how you want to use those types, ideally what you want is that you really, every definable set should contain a canonical definable type. So that is a type which is defined over the same parameters at x, and that actually does not depend on that choice of parameters. Because you can always do something very silly, which is if you have a definable set, you can take a point in it, and you can look at the type that says I'm equal to that point. This is going to be a definable type, but it's highly non-canonical, so that's really not what we want to do. And once again, the good news is that in VDF and SCVH, we can actually do that. So if we have a definable set, then we can find a definable type that contains the formula x is equal, x belongs to the definable set we started with. And this type does not actually, and this type is defined over any set over which x itself is defined. So this is one of those canonical definable sets. So just as a quick remark, actually in that proof, the prolongation construction is also extremely important because we actually build p omega first, and then from p omega we build p. So yeah, so in there the prolongations are also play a very important role, and there is a similar result for VFA0, but because of the lack of elimination of quantifiers in VFA0, we can't consider complete types anymore, and we have to consider quantifier-free types, and so it becomes more complicated, and I don't really want to talk about it. Actually, here we're also considering quantifier-free types, but it happens that they're complete types, so we can ignore that problem altogether. Alright, so if we look, what we have now is that it's a picture not too far from what we wanted to have at the beginning, which is that whenever we have a set X, we can find a type P in X, which is canonical in the sense that, well, it only really depends on X and not on the way we present it. And from this P, we can get a P omega, which, well, so this P is definable, and then we also get a definable P omega here. So, which is now an object that has nothing to do with the derivation. Sadly, it does not completely determine X, because we allow negations, and so weird things can happen. For example, if you have a ball, and you remove the little ball inside, the type you're going to consider is the generic type of the ball, which is going to be the same type you consider if you remove the small ball inside. So this does not entirely determine X, but it's already well, it's already not too bad. So I have a few minutes left. So so what I would like to do now is explain how this construction can be used to actually prove a theorem about these structures. Yes. Okay, so the theorem in question will be what's called elimination of imaginaries, which essentially is the property that every set has a smallest set of definition over which it's defined. So we have to be a little careful because, there can be problems because of definable functions, and so we have to be a little more precise than that. So we'll say that a set A inside of K is definably closed if it's closed under all definable functions. And now we can define properly what I just said. So a structure eliminates imaginaries if every definable set has a smallest definably closed set over which it is defined. And in that case, every definable type also has a smallest definably closed set over which it is defined. So do I already have an example? Yes, I did remember to put an example. So in algebraically closed field, and differentially closed field, you have elimination of imaginaries essentially because if you take an affine variety, it has a smallest field over which is defined. Which, if you look at it enough, is exactly what I wrote up there. Except I want it for all definable sets, so you have to work a little more, but it really comes from the existence of smallest fields of definition for varieties, or differential varieties. So remember, I'm working with valued fields, and in valued fields, in general, you don't eliminate imaginaries because, there are a bunch of problems. One of them being that, balls. Because if you have a ball, because it has no center, you can't really associate points to a ball to actually recover the ball. And so you have to actually cheat and add points to your structures, in particular add points for every ball. You need to add more than that, but a theorem of Haskell, Rzuszowski, and Raffeson tells us exactly what we have to add. So we need to add points for this, for these two questions, where this, if you look at it, is the moduli space for lattices of the valuation ring inside the field itself. And this is, another. This essentially is there to encode the reduces of those lattices, the redux of those lattices. And so I don't want to give a precise definition of it, but if we add points for these two quotients, we say that we're working in the geometric language. And so, so the theorem of Haskell, Rzuszowski, and McPherson is that if you have an algebraically closed valued field, it eliminates imaginaries in the geometric language. And so now let's look at what happens with our valued fields with operators. So the first thing we need to see is that in the definition of elimination of imaginaries, I asked for every definable set to have a smallest definably closed set over which it is defined. But it suffices to do that for classes of equivalence relations that are defined over no parameters. This is not too hard to see, but there is a little trick involved. And so once you see that, well, now you can actually, now X is going to be entirely determined by P omega, if it's a class of an equivalence relation. Because if you pick X, a class of an empty set definable equivalence relation, so I'm going to work either in VDFEC or in SCVHP. I can find this canonical P, which is definable, and then I can look at P omega. And so P omega is a type that lives entirely in an algebraically closed field. It's a definable type that lives in an algebraically closed field. So by Haskell, Rzuszowski, McPherson, it has a smallest definable set of definition A0. And it's not very complicated to see that A0 is also a smallest definable set of definition for P itself. And so once you have seen that, well, you can also see that you can actually reconstruct X from P, because X is exactly the set of things that are equivalent to a realization of P. And since P is definable, this is a way to define X from A0. Because remember, P is defined over A0, so this set here is defined over A0. Okay, so X itself is definable over A0, and it's not very hard to see that A0 is the smallest definable set of definition, because if X is defined over some other definably closed set A, then by definition of P, because we took it canonical, P is also defined over that A, and so A0 has to be in A, because it's the smallest set for P. Okay, so the conclusion is that in those two theories, we have elimination of imaginaries in the geometric language. Yes, I think I'm done, but I just want first to say that there was a third theory around, which was VFA0, that essentially disappeared after a while because of the problem with quantifier elimination. But Martin Hills and I are working at the moment on trying to deal with that, and I think there is a good hope that this theorem also holds for VFA0. And